Right, good morning everyone, and first of all thank you for giving up your Saturday morning to be here and accompany me in the journey of mathematics. My name is Eva Satmari. You probably seen me in the induction if you came, but just to remind you, I am the school's learning support officer, one of the learning support tutors or learning support officers. I am focusing on mathematics, so I do these workshops, sort of catch-up workshops if you have missed something, but I'm also providing one-to-one tutorials. So if you find a certain topic a little bit difficult, or you want to catch up on something that has done in September and you thought you understood, but now when it comes to the nitty-gritty parts of working it out, it seems to be a little bit more daunting than you first imagined, you're more than welcome to come and see me. If you can come in, that's probably the best, because it's quite easy to sort of explain things in person. But if you can't make it in, I can try to, we can organize it through Skype. It will be a little bit more difficult. Come on, just take a seat. The slides are just there. Skype is not as convenient as in person, but obviously Skype can work as well. It's better than nothing. So what else? Yeah, so my email address is in here, so just drop me an email whenever you feel like you need a bit more extra help. Now, two websites I would like to draw your attention to that gives you extra mathematics help, which you can look at it on your own at home, even at midnight, when I definitely will be sleeping. One of them is the Khan Academy, the other one is the Math Tutor. I don't know, however, you are of these two websites. The Khan Academy is an American website, but they have got pretty much every subject you can imagine. It starts with, it started out with mathematics, but now they do history and economics as well. So you can sort of check their economics videos out as well, but be aware of that it's an American website, so the context and the sort of examples they give might not be as familiar for you, because you probably see more of the British examples. The Math Tutor website, that is put together by UK higher education professionals who support mathematics at university level. So that's probably more of the same kind of teaching techniques than most likely taught in the UK. However, when it comes to, let's say, optimization and implicit differentiations and the rest of it, mathematics can be taught in so many different ways that it might not be exactly the same way as Tony have taught you. Just be aware of it, that there might be some slight differences. The Khan Academy has got a lot more topics on it. It's basically covering from basic addition up to college, university level mathematics. It's got linear algebra and the rest of it. The Math Tutor, it's a lot more condensed down to what is likely to come up in higher education. It's not as vast, and it doesn't really go into that much details at the basic levels. So probably the Khan Academy is the one that has got everything. The Math Tutor is very good at higher levels, but it's missing the matrix algebra. So there is no matrix algebra on maths, but there is matrix algebra on Khan Academy. Okay, there is a register going around here, so anybody else who needs to sign it, and the presentation, who doesn't have the presentation? And can you pass it to him as well? Okay, I'm experimenting with the camera. I'm hoping it's going to work, and I'm hoping that my microphone won't give up on me either. So hopefully the video will be up, not straight away, because this camera is pretty bad quality, so we're filming it with a separate camera, so it will take some time until my colleague can upload it. So we probably uploads by kind of Monday afternoonish, if you need to go through anything. Right, so what I'm trying to go through today is basically the first worksheet that you have been sort of doing. Go through a little bit in more details of the not necessarily just the examples, but the kind of theoretical background and the rest of it. Do a lot of practice questions on the different differentiation rules. And again, have a look at the applications in a little bit more detail. So the applications would be here marginal cost, marginal revenue, total cost, total revenue, and elasticity. Okay? Any more people need the slides? And there's a register somewhere as well, so if you could sign it, that would be great. Now, Stephen asked me that if people want to, at the end of the lesson, because the voice recording at Tony's lecture on Wednesday went bad, so if I could go through again the optimization in a little bit more detail. So I'm going to try to capture that as well, but in just a few details, because I've organized already a workshop which will be dedicated only for optimization in 2 weeks' time. So I'm going to go through the basic theories of the optimization, mentioning the inflection point and the rest of it, but there is a specific workshop which focuses on practicing those types of questions in 2 weeks' time, so I don't want to go into too much details to repeating myself, if that's all right with everyone. So, this here, the y equals f of x equals mx plus c, that is your linear graph. And this is basically why you went through it in September, just so you have a good understanding of what the basics are. So we call it a linear line because when you plot it, it's always going to be a line. Now, what is the importance of these two letters in here? I think Tony probably used the y equals ax plus b format. I'm not 100% sure. So this is the mathematician's way of using it, but what's important is that there is a coefficient in front of x. Doesn't matter what letter you use for it, it's a coefficient, it's a number in front of the x. What does that number do? What does that number tell you about the line? The slope. What is the slope? The gradient, it's another word for it. What does it do? What does it tell you about the graph? Steepness, okay? Otherwise, how fast it changes, okay? So with the linear graphs, one single number will always tell me how fast that graph is changes. And that's why the gradient is actually defined by change of y over change in x. Okay? So so when I've got a line in here, I've got 2 points, doesn't matter which 2 points those are. I've got corresponding coordinates on y and x. And if I look at this distance here, that is my change in x, which is basically just the difference of the x coordinates. And this distance here is my change in y, which again just the difference between the two coordinates. And if I divide these two numbers together for any one line, doesn't matter which 2 points I'm choosing, it's always the same number. So the gradient or the slope is always the same for a line. Okay? What does the c tell me? Or b in here? Which intercept? The y-intercept. So that's telling me the intercept here. Okay? Now, why is that important for me? What does that tell me here? What is the y-intercept telling me?
You know where y is when x is 0?
Exactly. So if this, the horizontal coordinate is 0, how much would I get from, in this case, y, but it can be price quantities whatsoever. So that's an importance in here. Okay, so that's why you've been kind of drummed to know about these things. Now, that's a linear graph, and that's the same for every line. So one particular line, one gradient. No difficulties about that. But we're not only interested in lines. Okay, so when we look at, let me just clear my board. So when we look at a curve, kind of curve, and I would be interested in how the curve changes at a particular point. Okay, so far I'm just talking about the point. Okay? How can I introduce that measure of change? So, if I look at this particular point, let's say x0, if I choose another point close enough, and I draw a line in between the 2 points, that's a very close approximation of how the curve changes around in this segment. A very good approximation, but not exact. It's still an approximation. So how can I make it better? Again, this would be a line. A line would have a gradient. Therefore, I would be able to give you some information about numerically how much the graph changes at that point. But again, it's just an approximation. How can I make it better? Well, bring this point closer. Now, that point is a lot more closer to the curve than this was. If I connect the two with a line, it gets a lot more closer to the curve, but it's still not exact. So what I'm going to do, I'm going to bring the second point virtually as close as possible, basically the 2 points being the same. But then what happens to this line? This line going to turn into the tangent. Okay? So for every single point on a curve, there is going to be one and only one tangent. What does a tangent mean?
It's where the two lines touch.
Exactly. So there is only one point where the curve and the straight line touches. Okay? And that very point is where I'm interested in the change. Okay? So that's my tangent. Thankfully, it's a straight line, so I can describe the gradient or the slope as the change at that particular point. Oops. So, but that is just one point, and as we know, every single curve has got infinitely many points. So that's not very helpful. However, the definition of the derivative is the limit of this change when delta x tends to 0. That has been briefly mentioned in the lecture, and this is not very important for you. It's important for mathematicians because this is basically the foundation of differential calculus. But you need to know that it can be applied, and thankfully over hundreds of years of mathematical work, applications have been developed. So what you need to actually understand is that basically for every single point these limits can be calculated, and then you build together something called the derivative function. And that derivative function is very good because that describes us point by point how any function changes.
So it's only when x tends to 0 or infinity?
Yes, 0, sorry. That's a big 0.
That's the question.
Pardon?
Can I ask a question?
Yes, yes, yes.
So when I was going through this in my notes, why is it when x gets close to 0 rather than y or the before?
Okay, now that's a good question. If you think about it, if this tends to 0, what's going to happen to the fraction? 0 divided by anything will always be 0. So if I make delta y to tend to 0, all I'm going to end up is a big fat 0 for everything.
Yeah.
So that's why that way it wouldn't work. So and again, the reason why I'm changing delta x, why I'm tending delta x to 0, is that I'm being able to, because this would be my x2 here, and this would be my x1. So I'm bringing this point closer and closer and closer. That means the distance I have to shrink smaller and smaller and smaller.
You also bring the y down.
Yes, but when I'm bringing that y down, what's actually happening, this becomes a line here, the tangent line. And if you look at the tangent line, that has got a number as a slope. And that's exact slope I'm trying to find in here. Which line which line is the slope corresponding to? Makes any sense?
Kind of.
Just
Yes?
repeat that definition again, the definition you just gave
Which one?
about the limits, the derivative.
What,
Said, as it tends to zero, that the words that you used, the exact phrase, I just want to hear it again.
the trouble is I don't remember now.
The
So-
derivative describes the
Change of the overall function. So the derivative is the change function, basically describing you how the function changes overall.
Yeah, but you also had that little bit about the limits. Just a good phrase,
so-
I just wanted to remember it.
I wish I remember now, but we can pick it up on the video, I'm afraid. We have to wait for that. Okay, now, one other thing about differentiation, that it has been developed by 3 different mathematicians over the history. So, depending on which textbook you look at it, you either see the Lagrange, the Leibniz, or the Newton notation. Newton's notation is probably the least familiar you've seen. It's most likely you're going to come up with it when you start to talk about differential equations, because the other two gets a little bit more cumbersome for differential equations, which is in mathematical economics. But these two are quite familiar, very commonly used for first-year calculus courses. I believe Tony uses the prime notation, and I prefer that as well. I find it a little bit more concise for single variable functions anyway. Okay, now, this is where you can't really make any shortcuts, okay? These are the rules you have to know by heart, okay? There's no other ways around it. Every single one of these rules have been derived from limits. Okay, so you can prove every single one of them using those limits theorems that I showed you. Luckily, you don't have to know. Oh, you've already got one. You don't have to know those proofs, but you do need to know the rules and how to apply them. So I made some copies of them. Okay, now on this table, which is also up on Moodle, if you go onto Moodle and you go for maths support resources or something along that way, and you go into the handouts, this is up in there as well. Now I put more functions in there that you probably will need, and none of the trigonometric functions are here because in economics you don't work with the trigonometric functions. So something like a to the x would be something like 2 to the x or 4 to the x. It's not one of those functions that you probably come across. And again, log-based functions is usually just the ln function, the logarithmic natural function that you come across with none of the other base functions. So there's about 4 rules here that you don't necessarily have to learn, but I thought it's kind of a good idea to give you a bit more than what you basically need. And thankfully I came here because I remembered I wanted to talk about 3 books. There is Tony's recommended list, and the Jacques book I use regularly and I really like it. The reason why I like it is pretty much covers everything that Tony does, and on top of that it introduces you to the mathematics separately and then explains how that particular mathematics is applied in economics. So it introduces the maths and then goes into the economics details. So I think it's very useful, especially if you haven't been very familiar with the economics terms. But that is just the terminology, the theories, and the rest of it, with very few practice questions. Now there are 2 books which have got worked out examples by the tons. One of them is Introduction to Mathematical Economics. Okay, this has got 710 fully solved problems. Okay, so you've got problem, solution, problem, solution, problem, solution throughout the whole book. It has got a little bit of theoretical explanation, it's very concise compared to Jacques. But it gives you extra practice if you need. I think that's also on Tony's recommended list. Now, this one I recently came across, and I asked the library, by the way, these 2 are definitely in the library, and there are more than a few copies. This one I recently asked the library to order copies. There is probably going to be 2 copies in the library. And this is Tamara Todorova, Problem Books Accompanying Mathematics for Economics. This book has been written to complement the Chiang book. Okay, the Chiang book is on the list. It's probably the most complicated one. That's the one that's also recommended at master's level. So anybody who's thinking about getting onto master's next year, probably it's all right. Probably would be helpful to get this book. And again, this is problems. So problem solution throughout the whole book. Now I checked on Google Books, and I think it's old enough now that you probably can have an electronic copy of it as well. But I don't know how expensive that is. If you wanted to get a paper copy, it's quite expensive. So I would only recommend to those people who are really serious about getting into the masters and they would be using it later on. Problems book to you know what? I'll just give it to you. Pardon? The Chiang book, Alpha C Chiang Mathematics for Economics, I think. Where is the register? Thank you. That's the slide. Oh, and the... Yes, of course. And, you know, anybody who wants to have a look at the books, more than welcome at the end of the session. So basically these are all the rules that you need to know, and there's no two ways about it. You have to know them by heart, because in economics you're not just told differentiate a product rule, use the product rule. You have to actually recognize which rule to use and when. Now, okay, let's look at some of the practice questions. So, okay, when I look at this function, what I've noticed is that it's a sum of two functions. So I remember that any sum and difference, I can differentiate term by term. The next thing I've noticed is that the first term is a power function. Okay? So, how do I differentiate a power function? And it's a workshop, so you're going to do the work, and I'm going to do the shopping. Okay, so what happens to the 2? Nothing, I'm just keeping the 2. Then what happens to the power? I'm bringing down the power. And what else happens to that power? -1. Okay? Power rule, you should be really well knowing it by now. And what happens to the plus 25? Why is the plus 25 become 0? Constant. Now, just to sort of give you the intuitive idea, there is a constant function here. That's what a constant function looks like. It's the same number regardless of the value of x. If you look at this function, what is the change of this function? How much does this function change? 0. Nothing. It doesn't change. So that's why every single constant disappears when you're differentiating. Okay? Now I need to tidy this one up a little bit. So 2 times -2 gives me -4/3x. I've got -2/3, take away 1 from there. -5/3. Okay? If you tend to get it wrong, one thing that you need to make sure that you just on the side of your paper write it out for yourself. Now, how can we subtract fractions? Have to bring them to the common denominator. Okay? So the 2/3 doesn't change. What is the common denominator? What is 1 as thirds? How many thirds do you have in 1? So 1 is always the same number over the same number. It doesn't matter what is the denominator. And because they both of them take away, that's why it becomes -5/3. Okay? Make sure that you kind of recap a little bit on fractions if you tend to make a mistake with these questions. Next one. Oops. What does this function look like? That's probably the wrong question to ask. So if you look at this function, you might have the impression that this is a fraction, this is a quotient rule. But at the top, you only have got a constant. And constant's derivative always going to be 0. So using the quotient rule here would be like shooting pigeons with a cannonball. But what do you remember? If anything is at the bottom, and here is why you went through all the rules of indices. You need to remember what happens if it's something down at the bottom as a power. What happens to the indices?
It's 1 over.
So what will be the power of this in here if I bring it up? Minus 1. Okay? Now, raising a power to a power, multiplying the powers together. So effectively what's happening, if it's a negative power at the bottom, it becomes positive at the top. And if it was positive at the bottom, it becomes negative at the top. So it will be 5x to the quarter. Now that's a lot more simpler. So if you know your rules of indices, differentiation can get a little bit simpler by manipulating complicated looking fractions or functions. So what is the derivative of this one then? Well, simple power rule again. Keep the 5, bring the quarter down, and then lower the power by 1. So that's 5 quarters. Remember, when you're multiplying fraction by a number, you're only multiplying the numerator, not the denominator. Okay? Think about pizzas. Just because you have more slices, that doesn't make any change or difference to the size of the slice. So that's why the denominator doesn't change. What will be the power? So I've got 1 quarter. I need to take a whole away from that. A whole is 4 quarters. 1 quarter minus 4 quarters gives me minus 3 quarters. Okay. Is that all right if I rub the board off? I just don't want to write in there because I'm aware of that there is a reflection of the light in there, so that probably wouldn't be coming out quite well on the camera. Now, what's the difference in this function compared to the previous functions?
There's not a constant?
What do you mean by that?
Not a number.
Not a number. Because, I mean, these are actually constants, but we don't know the values of them. So these are not exact numbers anymore. They're more kind of parameters, sort of. It's more like thinking about functions in general. Rather than one particular function, we're thinking about a function family. So if I change these coefficients into any number whatsoever, the rule would still hold. But still, we need to think about the rules that I need to apply. Again, I have got 3 terms here. I can differentiate the function term by term again. What kind of function is this? Even though I don't know the exact numbers, what kind of function do I have here? Power function. So again, I'm just differentiating using the power rule. So what do I need to do? Keep A, bring B plus 3 down, and what happens to the power? Minus 1. So B plus 3 minus 1 gives you B plus 2. How about this one? Minus Cx, what will that become? Minus C. Okay? Don't forget that x's derivative is always 1. Again, if you want to see y, you can just draw the y equals x function, and then you see that the change in there is always 1. What happens to the d? It goes to 0. Again, I don't know its exact value, but it's a constant, and constant function doesn't change. And the last one. Okay. What's the difference in here now? I have got 9 and 12 and the third, so I've got exact numbers. But what did I do to the variable?
You change it to...
I've changed it to u, okay? So the variable can be any numbers whatsoever, but you need to make sure that you know what variable you're talking about, okay? So to be precise, I should have written yu equals 9u to the third plus 12u, and that would exactly give you that this is actually the variable here. Okay, so, but that doesn't really, yeah?
The second one, derivative of y.
This one?
Can we say AB plus 3AXB?
If I wanted to, I can multiply the bracket out, but I would still need to keep the bracket.
Yeah.
Oops, not plus, minus c. Or I can go even one step further, and I can keep this multiplied by this and this multiplied by this. Up to you. I probably wouldn't bother because that takes up time, and the answer is pretty much equivalent. But that's the same. Okay, so what's the derivative of this function? 9 times a u to the minus 2/3. Again, 1/3 minus 1 gives me the minus 2/3. Plus what? Plus 12. Again, u is like the y equals x function. That's derivative is just 1. Tidy this one up. 9 times a third. 3u to the minus 2/3 plus 12. Okay? Pardon me. Right. The next kind of question is something that you have touched on when you talked about optimization. Basically, finding values of the first order derivative at particular points. Has everybody? So, for A, I have got f of x being equal to 4x to the 5, and I need to find the derivative at point 2, and I need to find the derivative at point minus 3. How do I go about it? What do I need to do? You're not used to talking, are you? I need to find the derivative function first, so I need to find the f prime of x. That's simply just differentiating this function. So what will be the derivative? 20x to the 4. And then what do I need to do to find f prime at 2? Substitute the x for 2. Pretty simple. So 2 times 20 times 2 to the 4. 2 to the 4. Okay, who said that? 320. Okay, I'm going to believe you because simply I'm just lazy to pick out my calculator. If you prove me wrong, that's fine. It's just a simple calculator question from here on. And if I wanted to do it to the minus 3, same thing. But now it's slightly bigger number. So probably better to try to use the calculator. So 20 times yes, 1620. Okay? Don't forget, this is your best friend from now on. Okay? Make sure that you know how to use it because it makes your life much, much simpler. Okay, the next function is 5 over x to the 2 over 5. Oops. Minus 7. Same thing, so what we need to do, we need to find the derivative function first. For that, what do I need to do to this function? need to change it into a power form. So what's going to be the power of x? Minus 2 over 5 minus 7. So I'm differentiating it. What will that tell me? I keep the 5, bring the minus 2 over 5 down, and what will be the power of x? Minus 7 over 5. Minus 7 again disappears because it's a constant. So what I need to do now is that substitute 2 for x. 5 cancels each other out, because if you multiply something and divide by something with the same number, that cancels down to 1. So it's basically minus 2 times 2 to the minus 7 over 5, and that's why the scientific calculator is very useful, because you can just type that into the calculator quite easily. And that is giving us the answer of minus 0.759 to 3 decimal, sorry, 7, 8. 8 to 3 decimal places. And I'm going to let you to play around with the minus 3 as a homework. Okay? So there is a question there asking, what have we calculated here? So what did we calculate here?
We calculated the slope when x is 2 and x is 3. Exactly.
So we now know exactly the value of the slope, which is giving me the change at that particular point. So it's giving me that the change at that particular point for this particular function. So for 4x to the 5 function, the change at 2 is 320, and the change at minus 3 is 1620. That gives you quite an indication about how fast changing that function is, to the 5 function. Okay?
So could we draw a graph from those 2 points?
Not necessarily, because these are the changes in this particular function. So I would know the slope of the tangent in here. As far as graphing concerned, that doesn't really help me. But if I use the optimization and found the minimums and the maximums, that would be a totally different question. Okay? Any more questions? So, product and quotient rules are coming up. Again, something that you have to know. Yes?
How can we multiply 2 into minus 7 over 5?
Using the calculator.
Oh, okay.
You have to use the scientific calculator, because otherwise,
Can we leave our answers just like that?
if it's an exact value that you need to calculate, which is probably in the optimization, the second order condition, you would need to know if this value is positive or negative. So you, by looking at it, I can say that it's negative. Because any positive number to whatever power always going to be positive, times a negative number always going to give me negative. So I can get away from not calculating it. But that's not might be the case in every single scenario. So if it's clear enough to be able to say it's positive or negative, and it's you using it for optimization purposes, fine. But if you can't really tell by looking at it if it's positive or negative, you would need to find the exact value. So I'm assuming that you all know the product and the quotient rule by heart now. So why do we call the product rule a product rule? Because you're applying it to functions that are a product of 2 different functions. And why is the quotient rule the quotient rule? Because you apply that to a function which is a quotient or a fraction of 2 different functions. So as you can see, mathematicians are extremely inventive people. They have got so many lovely names. basically it says what it does. So when I look at this function, when I need to differentiate it, I need to kind of recognize which function is which. So I would call this f, and this would be g. And again, the rule says differentiate the first term, multiply by the second, plus keep the first term and differentiate, multiply it by the derivative of the second. Okay? So, what's the derivative of x to the 2/3? What's the power of x? And I just keep g. Now I reverse the rows. I keep f, and I'm differentiating g. So what's the derivative of x to the 3rd minus 7? 3x squared, and the minus 7 disappears, so I can just keep it like that. There isn't much. Okay. I can probably tidy this up a little bit. So I could multiply these two out, because then what I can see is that minus 1/3 times x to the minus 1/3 times x to the 3rd, that would cancel down to quite a nice simple function. This would be still kept. And again, I could multiply these two out, so make the functions a little bit simpler. So there are no other numbers, so that stays 2/3. Now, x to the minus 1/3 times x to the 3rd, what will that give me? Okay, so x to the a times x to the b, what does that give me?
X to the a minus b.
Plus, if I'm multiplying them, I'm adding the powers together. Okay, but this is a negative number, so I need to add minus 3rd to positive 3. Positive 3 is how many thirds? 9/3. So 9/3 and negative 1/3 gives me positive 8/3. Minus 2 times 7 is 14 over 3x to the minus 1/3. Plus, what's going on in here? I'm going to keep the 3, and what will be the power of x? Now I have to add 2/3 and 2 together. The 2 would be 6 over 3. 6 over 3 plus 2 over 3 gives me 8 over 3 again. That's quite handy. Because now I can factor the 8 over 3 out. What's left behind is a 2/3 plus a 3rd. Two-thirds plus a 3rd. Yes. So that's 9/3 plus 2/3, 11 over 3. X to the 8 over 3 minus 14 over 3 times x to the minus 1/3. Okay? Now, in an exam situation, I probably wouldn't necessarily go into this one if it's just one of those rules that they're trying to test you how to use the product rule, because it's quite time consuming. So if you have got time for it, do go into it and make it as simple as possible. You would still have got the I'm not 100% sure how the exam is being marked. I don't know if you're being marked by demonstrating to know how to use the power rule, or also making it to the simplest. That's something that you would need to double check.
I'm very sorry, could I ask you to go through the simplification bit again?
Okay, so what I'm doing here, multiplying out. Okay, so everything by everything. So that's how I got here. X to the minus 1/3 times x to the 3rd. I'm using the rules of indices. When I multiply the same base, I have to add together the powers. So I'm adding together minus third plus a third. So that's minus third plus 3/3. Sorry, not 3/3. 9/3. So that's giving me the 8/3. Okay, so
plus the third.
yeah, so when I multiply these two out, that's how I got to the 8/3. Then I need to multiply these things together. Obviously the number doesn't have anything else to multiply with. And what I've got here is x to the 2/3 times x to the 2. So again, using the same rule, having to add the powers together, 2/3 plus 2, that is 2/3 plus 6/3, which is again giving me 8/3. So that's how I got to these two powers. And then what I see is that this can be factored out from both of these. Oops. So I can factor it out from both of those terms. And what's left behind is the 2/3 plus the 3. So 2/3 plus the 3. And again, if I add those together, 2/3 plus 3 gives me 2/3 plus 9/3. And that's how I got the 11/3. Okay? That was the first one. Okay, sorry.
That little bit that you just rubbed off the top of the x.
That was 8/3.
No, the next one. The next one. 14/3 and then x to the power of...
Minus 1/3. If you feel adventurous, more than happy for you to try the next one on your own while the board gets wiped. And then we can check if you got the same answer. Okay. Right, so the next one I'm not 100% sure if you have covered how to differentiate the e to the x function yet. But that's quite simple because that derivative is just the same. So e to the x is a special function. When you differentiate it, it becomes e to the x as well. So again, I'm using the product rule. So this is the first term in the product, and the bracket is the second term in the product. So I'm going to differentiate x to the 5. That gives me 5x to the 4, and just multiply it with the second term. Plus, leave the first term and differentiate the second term. The second term is 3x to the 5, so that derivative will be 15x to the 4, plus, as I said, e to the x's derivative is e to the x.
I don't see why e to the x.
You have to know.
It's just a,
This is just something to know. If you really want to know why, you would need to learn the limits and how to prove it.
so when I just did it like you asked, I just put x. To me, to my mind, it just made sense to put like x, e, then x and minus 1. Yeah. But I don't. So
There is a difference there, because e to the x is not x to the n. This is not a power function. Because for the power function, the variable is the base, and you have got a number in the power. This one is something called the exponential function. Okay, e is a number that is more or less about 2.71 something. It's a number. It's a special number. This is something like 3 to the x. So the variable is in the power, not in the base. So it's a different types of function compared to the power function.
Yeah, I think where I'm a bit slightly confused is that
Mm-hmm.
I thought x doesn't need to be called x, does it? It could be u, for example.
Yes.
So why?
Yes, however, this is the only variable in this particular function. There's no other.
Because it's the only one.
Yeah, and the e itself is always, e, the letter e, in this particular case is used for that specific number of 2.71 and then infinitely many.
Is it something like the pi number?
Yes, exactly. It's something like a pi, yes.
Quite often we see different letters on this course.
Yes. Okay,
When
now
it's E, it's different in another letter, is it?
you need to look at the function quite clearly. I mean, probably I should have been clearer by saying y equals f of x, and in that way you would know what's the variable and what's not a variable.
Okay. So that was u. So that was y equals u to the 5, 3u to the 5, e to the u.
Yeah.
The same, but just
Exactly.
down to the e.
Exactly.
So, are you saying that because all the other ones, the power is a finite number, 5 or 3?
Yes.
Whereas here e to the xx is a variable.
Yes.
That's the significant difference.
Exactly. That's a significant difference, that now the variable is in the power, not in the base. So that classifies it as a separate function.
Can the x be 1? E.
Okay, if I had e to the 1, that would be just a number to the first power, which is the number. So that's basically a constant. And your calculator has got the e programmed into it. So let's say if I end up with something e to the 3, I could use the calculator to find out the numerical value of that. So and that would be roughly 20.09 to 2 decimal places. Okay, on this particular function, to call the e, I need to press the alpha button and then the times 10 to the x. But it might be different on your calculator, so probably make sure. I mean, what's important here is it's the way that you can think about the e is something like 2 to the 3. That's a numerical value. So is e to the 3. But the difference is that the two base values are slightly different. But it still makes it a constant.
So, sorry, just to clarify for myself, in that equation, if e, instead of ex, it was like tx or something, then the correct way to do that would be like bring the x down, just do the power rule.
No, because that's still an exponent function. For that one, which you're not going to come across in this course, but for that one you would need to use the rule of a to the x on that. So that would be a slightly more complex differentiation. So as soon as the base is different to e, you can't use just the e to the x rule. As soon as the base is different from e, the e to the x rule doesn't apply anymore, because that's a slightly different function now. So if I had something like 2 to the x and I needed to differentiate that, which you're not going to come across in this course, I would need to apply a different rule, because this is a different type of function. What you need to remember is that if y is equal e to the x, then the y prime is e to the x.
And the second and third and fourth derivatives. Or
Yeah. It doesn't matter how many times you differentiate, e to the x just stays in itself. Now that's different if I end up with something like y equals e to the 4x squared. That would be different. We might come across that in a chain rule example. I'm going to show that in a couple of slides.
Is e to the x a unique thing, which is always...
Yeah, it's a unique function.
So is that the only thing which is always derivative always stays constant?
Yeah, not constant itself.
That's the only thing?
That's the only thing, yeah. But as long as you bring in a composite function for the e, that again changes. I probably went a little bit ahead in here. I'm afraid. Should have thought about it. Any more questions?
Is there a calculator you suggest we get?
Pardon?
Is there a particular calculator that you suggest we get?
I like the Casio ones. I would say any of the one with the natural display. Because the ones that have got the natural display, that's where the fractions look like fractions. Because some calculators, the display start to become something like 3R2. And that's supposed to mean 3 over 2. In the natural display, you see this. In a non-natural display, you would see something funny like this. So that's why I say try to get a calculator which has got a natural display. But if you really want to make, one thing is you can't use any programmable calculators, but a list of allowed calculators are on somewhere on the website. So if you go to Google, say BBK calculators, the page which recommends the calculators should come up. But most of them, the Casios are fine. The one that I have got is the Casio FX85ES, but that might be an outdated version. I had it for years. Let me just write that up on the board. I had it for too many years now, so it might not be available anymore. What's important is whichever calculator you get, make sure you get a natural display one, because that's easier to read, simply. If you're very used to your own calculator, there's no need for changing it. But if you're trying to get a new one, try to get one with a natural display. Okay? Okay, so the third one from the product rule. Now, there's a new function here again, ln x, okay? That is probably, again, not something that you talked about just yet. So if I've got the natural logarithm, now the natural logarithm is basically the e-based logarithm. I'm going to run a workshop on logs and exponents as well in a few weeks' time. That's probably going to be, well, maybe more than a few weeks, probably a few months' time. But that's going to be just dedicated for logs and exponents, to go through them again. But what's important for, as long as the differentiation goes, that if I differentiate the ln x function, the derivative will be the 1 over x. Again, why? You don't really need to know. You just need to remember that this is how the rule works. This is what the rule is. If you're really interested why, you can check out limits and see how that proof goes for this limit. But it's only if you have got plenty of time on your hand. So let's think about this function then. What do I have here? I have got 2x to the 2/3 multiplied by the ln x. So this is a product plus a third term. So this is not a straightforward product rule, but it's still part of the product rule. So I need to apply the product rule for the first term. and then I need to separately differentiate the third term. So in this one, that's my f, and that's my g. So I'm differentiating f, which will be 2 times 3 over 2 times x to the what power? Yes. So 3 over 2 minus 1, which is 2 halves, gives me the 1 half. And I'm keeping g, plus I'm going to keep the first, I'm going to keep f. And now I need to differentiate ln x. And as I said here, ln x's derivative is just going to be 1 over x. Plus, I mustn't forget about the third term, and that's derivative going to be 3ex. Again, the constant multiplier stays. E to the x is derivative e to the x. I'm going to have to revise this for next time. Okay, what I can do, I can cancel these two out. And what's going on in here? I've got x to the 3 halves times 1 over x. That is basically 2 times x to the 3 over 2 over x. And these are fractions. So what I'm going to do to the powers, or the indices. Oops. Okay? So that's again one of the rules of indices. If I have them in a fraction, I need to subtract the powers, and anything by itself is always to the first power. So that's going to be 2 times x to the half again. So that will be 2 times x to the half plus 3e to the x. And whether I factor out the x to the half or not, up to you. You can keep it this way and it's still a correct answer.
Sorry, could you do that again?
Which one?
Well, I suppose from that line.
Okay, so this one doesn't change. Okay, this one doesn't change. This one is 2 times x to the 3 over 2 times 1 over x. And that can be written like this.
For that, I would put 2x 3 over 2 times.
Doesn't make any difference. It's the same thing. If you have got 2 times 5 over 3, or if you've got 10 over 3, or 2 times 5 over 3, these are all the same thing.
I'm not sure. I'm not sure I got that. So I would put 2x 3 over 2 times x to the minus 1. Is that the same as what you put down?
Okay.
Okay, can you say that again? What you would say?
So 2x to the 3 over 2 multiply the dots and multiply by x to the minus 1.
Yeah, you can do that. But then what happens if you multiply the same bases?
Yeah.
What do you do to the powers?
Okay, so it's the same.
Add them together. So that's the same, 3 over 2 minus 1.
Yeah, okay.
That's the same.
Yeah.
Now, the differences here is that in one of the cases you use x to the a times x to the b equals x to the a plus b, and in the other case you use x to the a over x to the b equals x to the a minus b. Doesn't really matter. As long as you remember that anything that's undone at the bottom becomes negative when you bring it up, end up with the same result. Yes?
The 3x power of half,
Yeah?
can we say times 1 over x instead of ln x?
No? because in this particular case, for the product rule, remember the product rule first, this will be f prime g, and this is f g prime. So in the first case, I don't differentiate the second term.
Oh, yeah.
I differentiate it the second time. So you don't differentiate it both.
Okay, that's fine.
That's why that has to stay as ln x.
So 1 over x is the differentiated ln x?
Yes.
Another expression.
Exactly. So this is the derivative of ln x. Okay, so this is actually the final answer for that particular function. Okay, so that was the product rule. Let's have a look at the quotient rule. Right, can I rub the board off? Okay. Have you learned the quotient rule yet?
Yes.
Okay, tell me.
Start.
F prime of x, g of x, minus
Minus
fx
fx g prime x over x squared.
not x squared, gx squared. Okay, so basically differentiate the numerator, multiply it by the denominator, minus, keep the numerator, multiply it by the denominator's derivative, all over the denominator square. Okay, you might have seen it in different formats, but that's what you need to remember. So if I have got this function, what will be the derivative of this? So this is my f, and this is my g.
Tony started the bottom one when he did it.
Oh,
So I would do that. So I would start with the bottom one and do, so, sort of denominator, so, g to the x squared, which is, say, 2x plus 2, or in brackets, squared. And then he would put the, right back straight at the top, so the top left, so x squared plus 2, just written on the top left there, yeah. And then f prime x, so that's open brackets, 6x squared minus, then you would go, so it would be g1x, so that's 2x, and then it's fx, so that's then 2x cubed. Yeah.
Okay. Why can't I do it this way instead of that? Is there any difference? Multiplication is commutative, so it doesn't matter which term I start with. It makes no difference. Okay? So I can write it g times f prime or f prime g, exactly the same thing. So whichever is easier for you. Unfortunately, I was told that way, so I'm stuck in that way.
The minus should
Yeah.
make the positive one to be minus as well. Isn't it?
Yes, but I haven't broken up the bracket yet.
Okay.
So if I wanted to, I can go into manipulating, breaking it out, and making it simpler. And in that case, the minus, the plus one becomes negative. I'm not going to do that. I'm just not in the mood for it. So that's again f and g. So the derivative, again, anybody else would like to have a go at it?
X4.
X squared minus 2 squared. Okay, if I wanted to, I could multiply it out, but it's 2 terms. So I would need to raise the first term to the power of 2, which would be x to the 4. I would need to raise the second to the power of 2, which would be plus 4, but I still have got the multiple of the 2 terms. Because what I've got in here is a minus b squared, which is equal to a squared plus b squared minus 2ab. Okay? What I would do, keep it this way.
Okay.
For the denominator, just
Why is it minus?
this is just the denominator here. This is just the denominator here. So the denominator squared. We haven't done any differentiation yet. We just done the easy bit. So here comes the difficult bit. Okay? So what comes here then?
X squared minus 2.
Or 2x.
Is it x squared minus 2 or 2x?
Tony,
We love doing it this way.
Okay, let's take to Tony's way. So Tony would do differentiating the bottom. Okay? So how do you differentiate x squared minus 2?
Oh, it's 2.
It's 2x. And then 1 minus x squared minus. What comes next in Tony's way?
I don't think.
this isn't Tony's way. Tony's way.
Oh.
Start again on the top.
Yeah, Tony's.
There we go. So it'll just be to go.
Okay, sorry.
So if you want to stick to his way.
Right.
It will go x squared minus 2. Let's start with x
Yeah.
squared minus 2.
X squared minus 2, okay? Sorry, I'm getting confused with mine and Tony's. Okay, x squared minus 2, and then what do I multiply it with?
2x.
Minus 2x, okay? Because these comes together.
Oh, yeah.
Sorry, and then a negative.
What's the exponent you put that?
What is that?
Put on.
1 minus 2x.
Minus 2x.
What's the exponent?
Is a mistake.
And then it's 1 minus x squared.
1 minus
It's minus 2x.
Okay, so what we got here is g f prime, and then f g prime. Okay, what I can see here is that I can probably, if I multiply the bracket out, I can probably end up with something simpler at the numerator. So it's probably worth going into the algebraic manipulation for this particular one. Do you want me to show it, or are you happy to try it at home on your own?
Sure.
Okay. So now I've got minus 2x times x squared. Positive times negative gives me minus 2 times x squared gives me x cubed. And I've got minus 2 times minus 4x, that gives me positive 4x. Negative times negative gives me positive. Okay? Now, other thing I have got here is minus and a 2x. So that's again minus 2x times 1 is minus 2x. Minus times minus gives me plus. And x squared times 2x gives me 2x cubed. Okay? Check me, have I made a mistake or not? I'm only human. So what can we see now here?
The touch is 2x.
Yes, the minus 2x cubed plus 2x cubed cancels down to 0. And 4x minus 2x gives me positive 2x. So this overall function, although looked quite complicated, that is just 2x over x squared minus 2 squared. Okay? It doesn't always worth going into a long manipulation of the numerator, but in some cases you can probably spot that the powers would be the same in the x's, and then you would be able to make it simpler.
What are you looking for?
I've been doing mathematics for 20 years, and what I've seen here is that if I multiply these two out, I got x cubed, and would be x, and here x cubed and x. And that would tell me that from these many terms, I would probably end up with just maximum of 2. But in this particular case, they cancel out to even less. So just a quick evaluation saying, okay, if I'm multiplying out, would I have many functions with the same powers, or would I have got many different powers? Because if I end up with many different powers, that might not be worth going into. But if I do end up with similar powers, then that's probably make my expression simpler. Okay? Can I rub the board off? Okay, last one in the quotient rule. Okay, so that is g squared. Then multiply it with multiply the g, so that will be ln x plus 2x. And then what I need to do now is differentiate the top. Okay? Now, the top is a difference, so I need to differentiate it term by term. E to the x's derivative stays the same, so that will be e to the x. But what is the derivative of minus x? Minus 1. Then I've got the negative. And then what I have got left now is the numerator. And I need to multiply that with the derivative of the denominator. What's the derivative of the denominator? Again, it's a sum of two functions, so I can differentiate it term by term. What's the derivative of ln x? 1 over x. And what's the derivative of 2x? 2. Now, if I look at this, I am not 100% sure that if I go into breaking out the bracket, I would end up with something much, much simpler. So for now, I'm going to leave it like this. But you can have a go at it at home and see if it ends up with being anything simpler or not. Probably not too much simpler. Can be a little bit simpler. Okay, so that's the product and quotient rules. What's important is to notice when you need to use it. So is the function that you need to differentiate the product of two functions, or if it's a quotient of two functions, then you would use these rules. The next rule, which in most cases causes the most problems to students, is the chain rule. Okay? I wrote a expression that composite functions. Have you heard about it? That's the mathematical term. It might have been mentioned function of a function, one way or another. This is the case when you're using the chain rule. Now, composite functions are just the exact mathematical name of a function of a function. So basically, I apply g to x and then apply another function to the overall outcome. So, can you give me some examples when you're talking about functions of a function? Anything. In the worst case scenario, I just say it's not quite a function of a function. Nothing else is going to happen. Give me something you think about.
2x cubed. 2x cubed plus
2x cubed.
plus 2x 4.
Okay. This one is not a function of a function because I'm only applying functions to x, nothing to the, not composing everything together. It's not a composite function. It's just a sum of two functions. Another try.
X squared. Open brackets. G. Oh, sorry. Okay. Cross that out. Yeah. Two. Open bracket. Open other brackets. G plus 1. Close brackets. Close brackets.
Okay. What do you mean by g here?
Just another variable.
Okay. If you introduce another variable, then we start to talk about multivariable functions. And then this would be just a function of two variables rather than a composite of two functions with one variable.
Okay.
So that's slightly different again. But these questions are really, really important because this is when we sort of discover and kind of explore what you think it is and what it actually is. Anybody else wants to have a go?
Okay, so like open brackets, 2x plus 1, close bracket, squared.
Okay. What is the major difference between this and the others?
Brackets.
Well, this one has brackets as well.
The function inside is then raised to the power of something.
So what happens here is I'm applying a function. Basically what I'm telling you, okay, multiply my variable by 2 and add 1. That's one of my functions. That's one of my rules that I'm telling you to do. And then whatever comes out from there, raise that to the second power. So this would be my inside, this would be my g, and raising to the second power would be my f. Okay? Anybody wants to try another example?
Just like a to the power of 2, open brackets, b to the power of 3, open brackets, like c to the power of 4, and then close brackets.
I've got 3 different variables in here now, but all I'm doing is multiplying them together. So I can rewrite this as a squared, times b cubed c to the 4. That would be exactly the same thing here because it's just multiplication amongst them. So again, this would be one good example for a multivariable function. But this still doesn't make it a composite function.
2c, open brackets, 2c times 2c times 5, close brackets, to the power of 6.
Okay, now what's going on in here is I can convert this down to something simpler, because 2c times 5 gives me 10c to the power of 6, and then I can again manipulate it to be 10 to the 6 times t to the 6, c to the 6. Again, I ended up probably an even simpler function, because what's actually happened in here, I just have got one variables, and this is just a power function with a very big coefficient in front. So again, it's not the brackets that make the difference. Yes?
Open brackets 2x plus 4, close brackets to the minus 5.
Okay? So again, what I'm doing in here, I'm applying a function to x, multiplying it by 2, adding 4 to it. That's my g. And then whatever comes out from there, I'm applying the power of minus 5 to it. So I can't really simplify it down to anything simpler. So this would be the g, and this would be the f to the minus 5.
If I just said open bracket 2c close bracket to the power of 6, would that then make it no?
No, because that's again, if you get rid of the 5,
Yeah.
that would be still just a power function. Because I can again convert that down to, instead of 10, it would be just 2 to the 6 in here. If instead of multiplication you said add,
Yeah.
that would have worked. Now, is it only the power functions that we can use for making composite functions?
Apparently.
I could make a composite function by saying e to the 2x plus 1. Or I could make a composite function by saying take the log of 5x minus 2. Or it's a slightly different variation of the power function, because I could say square root of 2x minus 2. Or I could say, what can I write? Cube root of x squared minus 4x. So these are all composite functions. So what's the key in here is that there is a clear division between two different types of functions that's been applied at the same time. So the first type of function is this, the inside, and the second type of function is the cube root. In here, the first type of function is a linear function, and the second time is the exponent. In here, again, a linear function and a logarithmic function. Two very clear, distinct differences. Here, it's just the power function in a complicated format. This one again, altogether probably quadratic with two variables. This one is a linear function combined together with a quadratic. Okay? I'm hoping it kind of starts to sink in and make a little bit more sense, because it's important that you actually recognize when it's a composite function and when it's just another type of function.
I just see it as you've got, you just need to have a plus and minus and then
Okay.
which is essentially what it's done. Apart from if you get the log of the e, which I, to be honest, never really come across in my life.
Oh, okay.
That's what it's done.
You will in a few lectures'
I
time.
know I will, but I don't know. So yeah, it's, everything is you just put down plus or minus in, and then square it or cube or.
The then is a very important part in there. You also have got another type of function in there, so don't forget about that one. Okay, can I rub the board off? Okay. So, remember the rule the derivative will be differentiate the outside function at the inside place and then multiply it by the derivative of the inside function. So for this it's very important that I know which function is inside and which function is outside. A rule of thumb, the inside function is always the one that you are applying directly to x. So out of these two, I'm applying directly to the x the 5x plus 1, so that's my g. And then I'm applying the cube function, so that's my f. So f is my outside function. So I need to differentiate with respect to the cube, which is a power function. So I need to apply the power rule first. That will be 3 times something to the squared, and the something is what's inside the bracket. That's my g. And then I need to multiply this with the derivative of the inside function. Not very exact mathematical term, but probably the easiest to see intuitively. What's the derivative of the inside, which is 5x plus 1? 5. So that's how you end up with 15 times 5x plus 1 squared. And leave it at that. If you want, I probably wouldn't go into multiplying the bracket out, because then I just would need to do a lot more algebra and not necessarily ending up with anything simpler.
See, for that, could you cube everything inside the brackets? So 5 cubed, x cubed, and
you could, but a plus b to the cubed, that is a cubed plus b cubed plus 3 times a squared b plus 3 times ab squared.
Why is it that?
Is a plus b squared times a plus b.
Yes, of course.
So it's not that simple. So that's why in most cases you don't break out this bracket unless you're algebra wizard and you remember this, because then you can just differentiate it term by term and just using the power rule. However, it doesn't seem any simpler at all. So I think if you know the chain rule well enough, you end up with the derivative faster than if you apply the algebra and multiply it out. So sometimes multiplying the bracket out makes your life easier, sometimes makes it more difficult. Again, you will only know by practice. Can we move on to the next one? So y of x is equal to square root of 2x plus 1. Okay? So again, the function that I'm directly applying to x, g, is the 2x plus 1. And then the outside function is the root. Now, how do I differentiate a root? Is there any rule for differentiating a root? Exactly, there is no rule for differentiating the root, because every root can be rewritten as a power. So square root, what power is that?
2. Minus 2.
Half. Okay, so the nth root of x is the same as x to the 1 over n. So the root is always the 1 over power. Too many rules to remember. But if I see this, then the derivative becomes just again a simple power rule. So again, differentiate with respect to x, but using the outside function, which is the power. So bring down the power, keep the function as it is, and what will become the power now? Minus a half. Remember, a half minus 1 is minus half. And then I need to multiply that with the derivative of the inside, the derivative of g. 2x plus 1, what's the derivative of that? 2. So, what I can see that the 2 cancels out. So I end up with, okay, don't forget this is power, not multiplied. So I end up with 2x plus 1 to the minus half. If I really wanted to show off my understanding of indices and algebra, then I could say that this is equal to 1 over square root of 2x plus 1. Because negative power means I can bring it down to the bottom, and the half power means it's equal to the square root. If I really wanted to show off. That's the same. Rules of indices gonna come up all the time.
That particular rule, I don't think it's in what we've looked at. I know it's pretty basic, but like, half being the same as square root, I've not seen it on this course yet.
Oh.
I must have missed it. Was it? I thought I missed it. I was asleep.
A lot of rules.
Yeah,
A lot of rules, yes.
Can we say 1 over 2x plus 1 open bracket squared?
1 over
2x plus 1 open bracket squared. No, sorry, squared.
That's not the same, because then this would be 2x plus 1 to the minus 2.
Oh yeah, minus, can we do minus 2? Yeah.
That would be a different power in here. I would end up with minus 2 here if I started with minus 1 here. Okay? This is a half, so it's one step more complicated. Because the half power is the root. So square root of x is x to the half. Okay? Now, the last one, probably not the last one actually, the next one. So 1 over 4x minus 3 squared. So seemingly what happens, I have got chain of 3 functions. Okay, because I see, okay, there's a linear function here, I'm squaring it, and then put it over 1. So that looks like a chain of 3 functions. But I can condense these down to the power of minus 2. So this can be rewritten as 4x minus 3 to the negative 2. Okay, so I don't have the root now. So that's why it's just negative 2 instead of minus half. So if I differentiate this, then again I have got a power function and I've got a linear. So I bring the power down and what becomes of, what will be the new power? Minus 3. Negative 2 take away 1 gives you negative 3. And then I need to multiply it with the derivative of the inside, which is just 4. So I can make it a little bit simpler. Minus 8 times 4x minus 3 to the minus 4. And if I wanted to, I can write it like this, because the negative power means bring it down. I'm not sure how much Tony is actually using these ones in his solutions.
These will become really important important when you start applying it to economics, is that right?
I would say so, because then it would give you a bit more idea about how the quantity changes over time. Because at the moment these are just x's flying all over the place, but sooner or later you're going to relate them to prices and quantities. Any more questions? Okay. I have got more examples for the chain rule because I think that's probably one of the most complicated ones, and then we can look into some applications. Okay, let's make some space. Now, here, what is the inside function and what is the outside function? Which one is f and which one is g?
G is inside the bracket.
Sorry, talking about the top one? With the bottom one, yes, that would be.
G is
X cubed, yes, because g is the one that's directly applied to x. So to be able to calculate e to the x to the 3, I would need to know what x cubed is first, and then once I know that value, then I can raise that to the I can raise e to that power. So this is g. That means that the f is e. So when I'm differentiating it, the 2 stays as an invariant constants multiplier. E's derivative is itself, so that will be x cubed, and I need to multiply that with the g x cubed's derivative, which is 3x squared. And with the e functions, what we like to do is we like to bring out all the multiples in front and then just keep e as the second term. So 2 times 3 is 6x squared times e to the x cubed. Okay? Again, I'm aware of that you haven't covered e functions yet. So you probably will become familiar with them a little bit later in the syllabus. Just giving you a flavor here. And that reminds me that basically, if you have got, in general terms, functions like this, e to the f of x, which is basically you've got an e function and another function in here, a composite of 2 functions, then the derivative will be f prime of x times e f of x, which is basically showing us that this is a special case of the chain rule applied to the e function.
I don't see how you get if you go up to, I don't see how you get equal to 2ex cubed.
Okay, that would be this one. That would be this part, e of f of x. So this is the e of f of x part.
So the top one you looked at, yeah, the third one up, middle line there. Yeah. How do you go from there to equals, and then how that equals that?
Oh, okay.
Yeah.
What do I have here? 2 times e to the x cubed times 3x squared. So what can I multiply here together? Because if there is nothing in between, that's always multiplication.
Right.
So there's a host of multiplications in there. So the 2 and the 3 can be multiplied to be 6. And all I've done is just swap the order of e to the x cubed and x squared. Okay? It's been 2 hours now. No worries. This is exactly the kind of purpose of this workshop. That's why we're going in a such slower pace than the lectures.
Sorry, don't get the bottom thing bad.
That one?
Yeah.
It's a rule. Okay.
It's not the same as the chain pattern.
It's the same as the chain rule for applying the specific e to the f of x. The slight difference is here now that I've changed the notation around, because in the generic rule, f would be e and g would be the power. So differentiate the outside and then multiply that with the derivative of the inside.
And the example you did above, you did it the other way around.
Yes, because this multiple,
Yeah.
it's multiplication, commutative, makes no difference. If I got the derivative of the inside derivative first or the inside derivative second, makes no difference. But if you look at the final result, that's the derivative and then multiplied by the e of f of x. Okay? So now I've got the other new function. However, every time I see a root, I always have to rewrite that as a power because I don't have a separate rule for roots. So this is going to be rewritten as ln x to the half plus 3x. Okay, so again, this is now a composite function, a function of a function. Which one is g, which one is f? Which one is the function that I'm directly applying to x? X to the half plus 3x. So that's my g. And the ln is my f. Okay? So I need to differentiate it with according to the f function first. What is the derivative of a log? 1 over. So 1 over whatever is in there. 1 over x to the half plus 3x. And I need to multiply that with the derivative of g. So what's the derivative of g? Half times x to the minus half plus. Okay? Now, to make it look a little bit neater, I can multiply this and the numerator together. The numerator is just 1, so basically this becomes the top of the fraction. And then keep the bottom. And that's the answer. And again, apologies for bringing in something that you haven't really covered in details yet. Any questions about this one? Okay, I've got a few combinations of rules in here, and obviously this is how you're going to find the questions in exam and worksheet situations when it's not really being specified what rule to use. So you have to look at the function and see which rule to apply. So is that all right if I rub the board off? as a first function, what would you do to this function? Which rule would you apply?
Product.
Yeah, you could apply the product rule, but I would do something else. And the reason why I would do something else, because if I multiply the brackets out, I still end up with two terms, but two simpler terms. If I multiply this bracket out, that will give me 2 times x to the 4 minus 2 times x to the 6. And I believe you would agree with me that if I differentiate this, that is much simpler if I use the product rule. So sometimes, it's not the case in every single situation, but sometimes you can make the function simpler and therefore your life of differentiating easier. So if you're fine with the product rule, go ahead and do it. But mathematicians generally are very lazy and they're always looking for the simplest way and the simplest route.
But won't we be marked down if we did that? Isn't he just trying to...
Well, if he specifically tells you differentiate it using with the product rule, then yes, you would be marked down. But if he tells you differentiate it without forcing you to do the product rule, as long as you do the differentiation correctly, the function will be the same. Because if I use the product rule here, I would use the product rule, make it simpler, simplify it, end up with the same function if I differentiate it this way. So in practical situations, when it's a sort of function of an economic function, I would probably go trying to simplify it. You can't do it in every single case, but sometimes you can. So then differentiating this, it just becomes 8x cubed minus 12x to the 5. Very, very simple and quick. I strongly encourage you to go and do the product rule and convince yourself that you end up with the same function. Next function. What rule would you use here?
Invertible.
Yes. So I would bring them all up into the numerator. So this would be x to the minus 1 plus 2 times x to the minus 2 plus 3 times x to the minus 3. Okay? And then again, it becomes a simple case of using the power rule. And then that will be minus 1 times x to the minus 2 plus 2 times minus 2 times x to the minus 3 plus 3 times minus 3 times x to the minus 4. And then again I can rewrite that as minus 1 over x squared minus 4 over x cubed and minus 9 over x to the 4. Remembering the negative powers I can bring down. I could have kept them as negative powers, just multiplying out the constants. But
The bottom one's simpler than all of them.
because I don't have multiples of constants anymore. Whether you find x to the minus 3 or over x3 simpler, it's a personal preference. So you would be expected to multiply the constants out, but you wouldn't necessarily be expected to bring the power down to the fraction. But the constants you would have to multiply out. For me, it's just simpler to see that there is an inverse relationship in here, rather than seeing the negative power. But that's again personal preference. Okay? I'm going to need to make some space again. Is that all right? Okay, what rule would you use here?
Chain equation.
Yes. So I've got a quotient, but the bottom is a chain. So, right. What will be the bottom of the long fraction here? 1 minus x to the power of 6. Okay? Because the bottom you need to square, and when you're raising a power to a power, you multiply the indices together, and 2 times 3 makes 6. Okay? That's fine. And then you keep g, and you multiply that with the derivative of the top. What's the derivative of the top? Minus. You keep the top, and you multiply that with the derivative of the bottom. And that's a chain now, because it's a combination of a linear and a cubic. So I need to differentiate according to the cubic first. So bring the power down, lower the power by 1, and then I need to multiply that with the derivative of the inside. What is the derivative of 1 minus x?
Minus 1.
Minus 1. Okay, so don't forget about these negative ones, because they make the whole difference. So I'm just going to tidy it up a little bit. I'm going to swap the order around, simply because I don't like constants and powers being too close, because I tend to misread them, but other than that there is no difference there. But if I look at this, what can I sort of bring out altogether as a multiplier? So I've got the minus 1 times 3 times 3, and the negative sign in here. So negative negative makes it positive, and then 3 times 3 is 9.
Sorry, how did you get the minus 1?
The minus 1 is the derivative of the 1 minus x. In a chain rule, the numerator is a combination of a linear and a cubic function. So I'm differentiating according to cubic, bringing 3 down, keeping the power of 2, but then I need to multiply that with the derivative of the linear. And 1 minus x's derivative is negative 1. Okay? Again, what I can see here with the trained mathematician's eye is that 1 minus x squared can be factored out from both of them. And the reason why that would be good for me, because I could lower the power of the numerator down, the denominator down. So if you feel adventurous, try it at home and see if you can make it a little bit simpler. But I'm very conscious of the time. I'm already running over, so I'm not going to go into that much details. The next one what rules am I using here?
Exponential.
Yeah, so it's an exponential, it's a logarithmic, so those 2 rules. What else? Chain, and what else? Product. Everything. You got all of it for 1. So which is the main rule that I'm going by? The product, because it's a product of 2 functions. Okay? So I need to differentiate the first term, e to the 5x. Now that's a chain. So that will be 5 times e to the 5x. Okay? E to the 5x, the outside is the e function. the e's derivative is itself, and then I need to multiply that with the inside derivative, which is the 5x. But I like to keep the constants in front so I don't mess up the power and the constant. That's the only thing in here. And then this one was the derivative of the first term. I need to multiply that with the second term. Plus, I keep the first term, and I need to multiply that with the derivative of the second term. So ln 5x was the derivative of ln 5x. Again, the outside is the ln, the inside is the 5x. What's the derivative of ln? And then I need to multiply that with the derivative of the 5x. What's the derivative of the 5x? So the 5 cancels out. And then basically, that's all I have. 5 times e to the 5x times ln 5x plus e to the 5x over x. Again, I can't apply the rules of indices in here. I cannot, because this is x to the 1 and this is e to the 5x. So the bases are not the same. I can only apply the index rules if the bases are same. So if it was e to the 5x, e to the x, I could use the power rule. If it was x to the 5 and it would be x, I could use the power rule. Sorry, the rules of indices. But because it's two different powers, I can't use the rules of indices.
So did you say there was e to the 5x and e to the x?
Yes. Yeah. So we use the chain rule here when we differentiated the first term, and we use the chain rule here when we differentiated the second, here when we differentiated the second term, because both of them are composite functions.
Could you tell me again, sorry?
So I use the chain rule here when you differentiated e to the 5x,
Yeah.
and I use the chain rule in the second term when I differentiated ln 5x. And these two long terms are the products, the rule of products. So this is f prime g, and this is f g prime. Okay? Can I rub the board off? Okay, let me just make this one and I'll leave that one up.
So the f, that bit, the f prime g is,
Yep.
is that whole term.
Yeah, this is the f prime and that is the g. And this is the f. Oops, doesn't look very nice. This is the f and that is the g prime. Because this was f and this was g. I'm aware that I'm running over time, so anybody who needs to go, please feel free to stand up at any point and leave the room.
Can I just ask where the 5 comes from?
This one,
Yeah.
this 5, that is the derivative of the 5x. So it's e to the 5x, so I'm differentiating with respect to the e. No, that's the wrong, sorry, ignore that. The first derivative, the outside function is e, and e's derivative is itself. So that's why it stays e to the 5x. But then the inside derivative, 5x's derivative is the 5. So that's where the 5 comes from. Any more questions? Okay. So look at this monster. okay? Because this is definitely a monster. What kind of rules are there? If I'm just looking at it, what kind of rules I would need to use? Quotient? Chain? And unfortunately, I would need to use the chain twice, because I would need to use the chain in the case of the ln. Then when I'm doing the inside function, that would be a quotient. But within the quotient, I still have got a chain, because this is the root. I guarantee you that I will screw up. I will definitely make a mistake somewhere. But however, and again, I'm a little bit ahead of myself in here, because you probably haven't covered logs yet at all. But if I know the log rules, I can make this function a lot simpler. So the log rules, this particular log rule, if I have got a fraction behind the log, I can break that out into a difference of the logs. And this is one of the situations where the power or the importance of the log function lies. It can make complicated functions simpler. There is another log rule that I'm going to use in here, and that if I have got a power behind the log, I can bring that out as a multiple into the front. And probably just to be concise, the third log rule, which is probably going to be introduced as the first log rule, is if I have got a multiple behind the log, I can break it out into a sum of the logs. This comes from the fact that logs are a different way of thinking about powers. And remember, when you multiplied the same bases together, you added the powers together. So that's where the adding rule comes from. But again, I'm running ahead a little bit. So these are the log rules that you will need to remember, and these two I'm going to use. So instead of going in with the big guns, trying to apply all of those different chains and quotient rules, I'm going to make my expression simpler, so I will be able to differentiate it easier. So the first log rule I'm going to apply, this is A, this is B. So it will be ln 4x minus ln square root of x cubed minus 3.
So which is A and B again? What's A and B?
This was A, the top is A, and the bottom is B. Because that's what I'm doing here. But what I notice here is that it's a square root. So the first one I'm going to keep, but this one I can rewrite as to the power of half, because a root is the half power. And then that means I can apply this rule, and the power I can bring out in front of the log. So ln 4x minus a half times ln x to the cubed minus 3. Now you might not agree with me that this is simpler, but what you have to agree with me on, that differentiating this is simpler. Because now I have got two terms and only simple chain rules instead of chain rule combined with quotient combined with chain. So differentiating this, term 1, ln 4x. How do I differentiate the ln 4x? 1 over 4x.
Cool.
Yes. So the log function is the outside function. The 4x is the inside function. The log function's derivative is the 1 over, and the 4x's derivative is the 4. So that term done. And I can actually see I can cancel them by the 4. Half stays. And again, what I've got here is a chain of a log. Same rule, keeping in mind that the inside function is different.
Why is if ln is 1 over x, then why is it 1 over 4x?
Because it's the chain rule. So it was f prime at g of x times g prime of x. So the derivative of the log is the 1 over at the place of g, which is the 4x. So, and same here, the f, the outside is the log at the inside place. So it will be 1 over x cubed minus 3, and then I need to multiply that with the inside's derivative. And x cubed minus 3's derivative is? Okay, so what I ended up with is 1 over x minus 3 over 2. Actually, I'm just going to put it all in one fraction. Okay, so numerators multiplied together, 1 times 1 times 3x squared. 3x squared over 2 times that. So I either keep it like this, or if I feel like I could multiply it out and it would be 2x cubed minus 6. Same. Depends on your mood. Okay? That was probably a marathon for today. Okay? Are you still in the mood for looking at some economic applications? I've got 2. So Firm's demand function is Q equals 30 minus 2p, and the total cost function is Q cubed minus 2Q squared plus 6Q. Question: find the average and marginal cost functions. So the average cost and the marginal cost are the questions. Okay? How do we calculate the average cost? Total cost divided by the quantity. So what we need to do is just need to look at the total cost function and divide that by the quantity. So what can I see here? Every single term in the numerator have got Q. So I can simplify them by Q. Q cube's power, if I cancel that down by Q, becomes Q squared. Q squared powers becomes Q, and Q becomes 1. Then I'm dividing it by Q. So it's basically Q cubed divided by Q, Q squared divided by Q, and Q divided by Q. So the average cost becomes Q squared minus 2Q plus 6. Marginal cost.
First derivative of total.
With respect to quantity. So the derivative of the total cost with respect to the quantity. So what's the derivative of the total cost?
3Q squared minus 4Q plus 6.
Okay. Nice and simple power functions, nothing too complicated. in B was the total revenue. How do you calculate total revenue?
P times Q.
P times Q, price times quantity. Now, I'm looking ahead, and the next question is find the marginal revenue function. What is the marginal revenue? The total revenue, the derivative of the total revenue with respect to quantity. So the total revenue, I have to express it as a function of Q. I was given that demand function. That is not the function of Q. That is the function of P. So what do I need to do? Because if I use this and substitute back into here for Q, I end up with the total net revenue expressed as a function of P. And then I wouldn't be able to do anything with it when it comes to doing the marginal revenue. So, what I need to do to this? Yeah, rearrange it. So, 2P equals 30 minus Q. So P is equal to 15 minus half a Q. Is everybody clear on how I ended up with that? I could have said 0.5, makes no difference. And now, I can express the total revenue as function of Q. So that will be 15Q minus half Q squared. Okay, so that's my total revenue. Oops. The marginal revenue, as we mentioned, is the derivative of the total revenue with respect to the quantity. So what I need to do now, I need to pick up the total revenue function and differentiate it with respect to Q. So what's the derivative of this then? 15Q's derivative is 15 minus half times Q squared. What will be the derivative? It's just Q, because half times 2 makes it 1, and Q squared becomes Q. Quite simple. And what is the firm's total profit function? No, that would be profit. That would be a condition for profit maximization for a competitive market. That's very different. The total revenue, the profit is always the difference between the total revenue and the total cost. So the total revenue is this one. And I need to take away from it the total cost, which was given here. So take away Q cubed minus 2Q squared plus 6Q. Now I suggest that you always put the whole total revenue function into a bracket with the negative in front. Because if you try to take it away term by term, you might forget about changing the sign by the last term. At least I would. If you're confident and never screw it up, fine, go with it. But I know myself, and I would definitely forget one of the signs. So then I can break out the bracket. Negative in front of the bracket means that everything inside changes the opposite sign. So Q squared becomes Q cubed becomes negative Q cubed. Minus 2Q squared becomes plus 2Q squared. And positive 6Q becomes negative 6Q. And I'm gonna need to make some space up here just to find the profit function at the end. what I've got in here, 15Q minus 6Q. What does that give me? And I have got negative half Q squared plus 2Q squared. What is that going to give me? 1.5Q squared. And I only got one cubic term, so I just copy that down. Okay? And that's it. Hello.
Hello. Please, finishing to examine esto.
1:30.
Yes.
What does it mean? We need to finish now. You need an hour to get it ready.
It's okay.
Okay.
Pero examinator, please.
Okay.
Okay?
Okay.
Thank you.
Oopsie. Okay. Last question. Okay, so I've got Q equals 25 minus 2P cubed. And find the own price elasticity of demand and evaluate this. Oops, that was supposed to say, I don't know what went wrong there with the PowerPoint. Evaluate this at P equals these different values. Okay? So, how do you find the own price elasticity? Not data.
DQ dp times P.
Now, you either use the negative sign here or you don't. Okay? If you don't use the negative sign, you're most likely going to end up with negative numbers. And depending on if you want to find out if something is elastic, inelastic, or unit elastic, you would compare it to -1. If you bring in the negative sign, then you would compare it to +1. Okay? So if you ever have to compare things to being elastic, inelastic, or unit elastic, be aware of that by not using or using the negative sign, you would compare it to different values, positive or -1.
And it doesn't matter.
It doesn't matter as long as you use it consistently. So if you use it positively, then you compare it to -1. But if you use the negative value, you compare it to +1. That's the important thing in here. And again, you need to remember which one is elastic and inelastic.
So you said if you use the negative, you compare it to a positive.
+1. If you use the positive one, you compare it to -1. Okay, so what are we going to do here? This one is dq/dp, so I need to differentiate this with respect to p. So what's the derivative of this with respect to p?
6p squared
Minus 6p squared, and I need to multiply that by p over q. At the moment, I'm just looking for the elasticity of demand without looking at it at different prices. In a sense, I'm just looking for an expression for the elasticity of demand. Okay, so that's the derivative, and then multiply that by p over q. So altogether this will be negative 6p cubed over q. So that is the elasticity of demand, sorry, the own price elasticity of demand. Now, I've got p equals 1/2, p equals 1, and p equals 2. That's useful because I can substitute that back into the own price elasticity expression But what else do I need? I need the values of q. So how am I going to find the values of q? Substitute it back into here. Okay? So if q is half, sorry, if p is half, then q will be 25 minus 2 times half to the cubed, or 25 minus 2 times 1 cubed, or 25 minus 2 times 2 cubed. I have to pick up the calculator. So 25 minus 2 times half cubed. So the q here give 99 over 4. 25 minus 2 times 1, which is 2. That's 23, that's for the easiest. And then 25 minus 2 times 2 cubed, that's 9. And then now I know the values of p's and q's, so I can calculate the value of the elasticity, the own price elasticity. So that will be minus 6 times half cubed over 99 over 4. This will be minus 6 times 1 cubed over 23. And this will be minus 6 times 2 cubed over 9. Again, you can put that into the calculator. See if it's bigger or smaller than -1. And then you can decide if it's elastic, inelastic, and it's definitely not going to be unit elastic because none of them is going to be equal to exactly -1. Okay, this is what I planned for today. Okay, and I've been asked by Stephen to have a look at the principles of optimization. But as I mentioned at the beginning, I'm going to have a workshop purely on optimization in 2 weeks' time. So are you up for looking at the principles a little bit, or you're absolutely shattered? Let's do it. Okay, anybody who feels like had enough, feel free to go.
We're going to do this in 2 weeks' time.
We're going to do it in more details. Now I'm just covering the theory, and I'm going to show you the practical examples and the practice questions in 2 weeks' time.
I've got an appointment.
Well, I have to get out here as soon as possible because they got an exam, so I'm going to try to do it in 10-15 minutes. So what you got here, you got a function, something like this, okay? Minimums and maximums, that's obviously a maximum point, that's obviously a minimum point, that's another maximum point. What you can see in all of them, that the tangent at this particular point is a line that is parallel to the x-axis. That means that the derivative at this particular point, which I'm going to call x1, is 0. 0 means no change, and therefore we call it stationary points. So every point where the change is 0, which is the first derivative is 0, that we call a stationary point. So this one, which is a different point, the first derivative here is also 0, and here the first derivative is 0 again. But if you look at this, that's a plateau here, a kind of straight line. So this, the derivative here, would also be 0. However, clearly, this is neither a maximum nor a minimum. So this is what we call a stationary point of inflection. Okay, because in here, the change is 0, but it's clearly not a minimum, not a maximum. So I'm going to have to drop the board off. Is that all right? So that's why the first order condition for every optimization is to find a first order derivative and set that equal to 0, and from that equation you will have possible minimums, maximums. But that's not enough, because just knowing that I have got the first derivative being equal to 0, I still have at least 3 different types of points I can end up with. So that's why I need the second order condition. And what does the second order condition tell me? If the second order derivative at that particular point I'm interested in, is negative, then what do I have?
Maximum.
If the second order derivative is positive at that particular point, what do I have? A minimum. And what happens if I have got if the second order derivative at that particular point is 0?
It's a
possible point of inflection. So this is a necessary condition, but that's not enough. So what do I need also to make sure that this is a point of inflection? The third derivative of that particular point is non-zero. So then I have got definitely a point of inflection. Now, I've got 2 types of points of inflections. One of them is the stationary point of inflection. So the second order derivative there is 0. The third order derivative is not 0. But the first order derivative there is also 0. Stationary. And the non-stationary is where the first derivative at that particular point is not 0.
The first type is when it's first derivative is 0,
yeah,
then it's a stationary.
Yes. Not forgetting that the second order is 0 and the third order is not.
Yes.
And again, for points of inflection, second order is 0, third is not. And if the first is neither 0 again, that's a non-stationary point of inflection. Okay? And there was something mentioned about the nth test. Okay? Because just by this, I can end up with somewhere here that the third derivative is still 0. So the nth test, what is the nth test? I'm differentiating and differentiating and differentiating until I end up with something that is a non-zero derivative. Okay? So I'm differentiating n times, and at that particular point, I end up with a non-zero derivative. Okay? If n is odd, 3, 5, 7, rest of it, what did I find? Point of inflection. If n is even, then it's a minimum or a maximum, depending on if that particular derivative is positive or negative. So minimum when f, the derivative is positive, and maximum if the nth derivative at this particular point is negative. And I'm afraid I have to go. Okay? Anybody who feels like wants to know a little bit more about it, email me and we organize an appointment, okay?